சார் பேனர் இருக்குல்ல உங்ககிட்ட, நீங்க போட்டு விட்டுருங்க.
அதான் பேனர் தான் தேடிட்டு இருக்கேன்.
இப்பதான் மெயில் பண்ண உங்களுக்கு.
ஓ பேனர் கூட பண்ணீங்களா? சரி. ஓ ஓகேவா பாருங்க.
சார் இது போதும் சார், நான் சைன் அவுட் பண்ணிடுறேன்.
ஓகே
5:15 அவங்க வந்தோடனே போட்டு விட்டுருங்க. அது நான் 5:30க்கு ஃபோன்ல மாத்தி விட்டுறேன் சார். நான் இப்போ கட் ஆயிரும், நான் வச்சிடறேன் சார். ஓகே, தேங்க்யூ சார்.
Do you have the hunger to build your dreams, to make them come alive, to challenge yourself
Good evening, sir.
Good evening. Good evening.
Venugopal, sir.
Very good. Yeah. Yeah. So, call this just below.
Sir, check. Are you able to share any PPT, sir? Because I'm not giving any. That is, I allowed all the panelists to present, make them present.
Yeah, let me try. Yeah. Can you see something?
Yes, sir. A warm welcome to all.
Yeah. Then it's fine.
Okay, sir.
So yeah, I think that's why I'm trying to call this fellow. Have you sent him the link, Professor Pandey?
Oh, you want the link, sir? Can I forward it again?
No, I have the link. Whether it is sent to the professor or not, that's why I'm trying to call this another faculty. Because that was his responsibility to send.
Maybe Venkat Noori sir sent, sir.
Yeah, Nori said he told somebody else to send it. Now, I don't know. Then let's
Okay. That's why.
This is all problems, People
Yes.
people give work to somebody else. That's the problem. Delegation. No problem. Too many problems. That's a bit of a problem. I think. Well, it's just window thing. Just window thing. हेलो
यस नमस्ते सर।
हाँ वो अभी वो जो आपका स्टेट आया था पैनल लिंक्स का वो भेजा है ना उनको पांडे सर को।
हाँ जी भेजा हुआ सर मैंने।
हाँ ठीक है उसमें से डायरेक्ट लिंक क्लिक किया तो डायरेक्ट ज्वाइन हो गया।
हाँ जी सर हाँ जी मैंने भेज रखा है।
हाँ नया जो 7 लोगों का पैनल लिस्ट आया था वो भेजा है ना नया।
हाँ जी जो अभी बाद में आया था लास्ट में वही भेजा है।
करेक्ट ठीक है और ठीक है Yeah, he has sent it.
Do you have the hunger to build your dreams, to make them come alive, to challenge yourself, and to evolve as a champion? Welcome to SRM AP.
It wasn't long ago when I joined SRM AP. It was my first day about 3 years ago when I stepped my first foot on this campus, extremely nervous and confused about how my life is going to shape in this university. However, I was astonished by the people that I met on campus, people that come from such diverse backgrounds, people that have done so much, and all of them share one love for technology.
It's like for every 10 students, there's one faculty, which helped us develop a bond with the faculty and led to personal mentoring.
From internationally trained faculty to world-class infrastructure and practical learning curriculum, SRM AP is the one right stop to shape your future. The students from our maiden batch have emerged as successful entrepreneurs launching RI.ai with an investment of about $1,20,000.
SRM has given us a plethora of opportunities for us to pursue. From startup semesters at UC Berkeley to multiple international hackathons, that has helped us travel the world and reap the benefits of a large network and really get out there and put ourselves and make a mark.
There are students who are building industry level projects right out in college in the first and second years. I haven't seen people outside who probably build this scale of projects and actually get this executed and deployed in industry.
Getting a job at PVP Japan, the strategic partner of Google Japan, was really a dream come true. The curriculum at SRM University AP is a perfect blend of both theory and practical knowledge. They mold us from being mere students into very good professionals. We were the first cohort from SRM AP to visit the University of California, Berkeley. When we started participating in competitions and hackathons, we were winning against students from Harvard, Stanford, MIT, students from UC Berkeley itself, and these experiences made us break down all our mental barriers.
We provide a wide range of opportunities for our students and facilitate them to pursue higher studies at top QS ranking universities across the globe with scholarships.
I am Sriharsha.
I am Rahul.
Hi, this is Harini.
I got an admitted Newark University with a scholarship of $16,000.
I got admitted to University of Michigan with a $26,000 scholarship for my whole course.
I have got admission in University of Texas Arlington.
Everybody has something to offer here. Everybody has ambition. SRM AP acts as a catalyst to your passion, be it entrepreneurship, higher studies, or placements.
Here at SRM AP, you can be whatever you want to be. If you are a dreamer, this is the place where your dreams are nurtured and encouraged.
SRM AP. Embark on the avenues of excellence.
Hello guys.
Hello.
So Jasinder Singh, you're on campus or?
No, he's. I think he's entered something near Mangalgiri. What? Entered the apartment there.
Okay. Yes.
Mangalgiri.
Okay, he's in Mangalgiri. Okay, he stays in Mangalgiri. Fine. या सर जी एक बार हम लोग व्हाट्सएप में डाल दो सर सबको।
हाँ डाला मैंने।
2018 सबको डाल दिया।
हाँ।
ओके अभी देखना, अब तक देखा नहीं मैंने।
डाला है।
एक्स स्कॉलर्स को डाला है 2019 2018 ना। और हमारा एमटेक स्टूडेंट्स को डाल देना सर।
हाँ एमटेक का भी ग्रुप है ना, उसमें डाला है।
हाँ ओके, आई एम नॉट इन दैट। सो 2020 को भी चलेगा ना सर? वेरी गुड।
सबको चला गया। अभी कितने, अभी तुम्हें ज्वाइन नहीं हुआ है?
लोग कब आएंगे नहीं मालूम।
ये प्रॉब्लम वही है, ये बड़े-बड़े लेक्चर बड़े लोगों को बुलाने का, और ये ज्यादा लोग ज्वाइन नहीं हुआ। नहीं ये एक्चुअली वेनु सर, आर यू देयर?
Yes sir, I am very much available sir.
So what I'm saying is the outside university people can join, na, easily?
Yes sir. It is already open sir. Whether if they register with a link, provided link, they can able to join easily.
Okay. Yes.
Hello sir. Sorry sir. Good evening.
Good evening. Sorry sir. Because that's what we are worried, because we invite these big people and we have to have at least 100 people audience, otherwise it's a problem.
I will inform you how many register. I will inform you, sir. 2 minutes.
Yeah. Okay.
Sir, इस टाइम में क्या किया मैंने? I didn't put any registration link, sir. I gave them direct joining link because many people will not go and click there and register also.
Yeah. True.
So they can directly join, no registrations.
Yeah, fine. Anyway, we have to get some 100 to 200 audience.
Yeah.
Otherwise, it becomes difficult.
Correct, sir. So, आरी भरकम orientation करवा रहे हैं students undergrad.
Orientation is 23rd starting orientation.
Sir, how many students are mechanical finally?
They are saying 11 students.
11, okay, not bad. To start. Maybe another 20-30 will join us, sir. Easy say.
Yeah, it will.
Yeah, 40-45 is good, sir.
Yeah, fine.
अभी तो 2 सेक्शन मुश्किल है, 1 सेक्शन भी लगाए तो अच्छा ही है.
हाँ, 2 सेक्शन तो मुश्किल है. Okay, people started coming in.
Yeah.
Oh, we should put in our faculty group also, no?
Good evening, sir. Pandey, sir.
He's on mute, I think.
Good evening, Pandey, sir. I think mute hai.
Yeah, yes. I think he's on mute.
Yeah, just send a chat message.
Yeah.
He has to connect to the audio, sir.
Yeah, I think. I think Dr. Jaswinder, you can call him maybe. Yeah.
ठीक है सर. तो यहाँ सर आपकी आवाज नहीं आ रही. ठीक है सर. हाँ जी सर. हाँ जी. सर वो दोबारा ज्वाइन करेंगे. आई थिंक नेटवर्क इशू आ रहा है.
ओके.
हाँ जी सर.
Sir, I
Yeah.
can see BC office Navamani in the attendees.
Oh, is it?
I don't know if this is
Yeah, he's not a panelist. Okay, yeah, he's joining, but yeah.
Yes, sir.
Yeah, fine. So, which is joining, sir?
पांडे सर आपका माइक म्यूट है. आपका माइक म्यूट है सर.
हेलो.
यस सर.
Hello, sir. Yes, we can hear you now. Welcome, sir.
Thank you.
Thank you so much, sir, for accepting our invitation. In the past, we used to ask like, how was your journey? Was it comfortable? How was your stay?
Yeah.
Those questions.
Now it's all online.
Yes.
Okay, we'll just wait for a couple of minutes, then we'll start.
Dr. Nori VC sir has joined in. Thank you.
Oh, okay. Thank you very much. So, can we start?
Yes, sir.
Yeah, it's my pleasure. Thank you.
Thank you, sir, for joining.
Thank you.
Yeah, good evening, everyone. Yeah.
Good evening. Yeah.
Okay.
Good evening.
Yes, sir. Good evening, everyone. Welcome to the Mechanical Engineering Department's Distinguished Lecture Series. I request Professor Prakash Jadhav, HOD of Mechanical Department, to give the welcome address.
Okay. Thank you, Dr. Nori. On behalf of SRMAB Mechanical Department, I extend a warm welcome to all of you for the distinguished lecture series. I welcome our Honorable Vice Chancellor, Dr. V.S. Rao. And I also welcome our distinguished guest of today, Professor Pulak Pandey from IIT Delhi. I welcome all the participants. The topic of the presentation today is very interesting, additive manufacturing. I hope everybody will enjoy the interesting discussions. Professor Pandey sir, just for the information, our university started 4 years back, and our department is also now 4 years old. First batch has just graduated. We offer BTech, MTech, and PhD programs in mechanical engineering here. And we currently have 10 faculty members in mechanical department. And all the faculty members are PhDs from either IITs or abroad. We do have some DST projects running in the department, as well as we do have industry sponsored projects also running in the department. So we'll be happy to hear from you about your research areas and would like to collaborate with you through Dr. Jaswinder. Thank you, sir. And once again, welcome all.
Thank you. Thank you, Professor Prakash Jadhav, for the welcome address. Now, I request Honorable Vice Chancellor, SRM University AP, Professor V.S. Rao, to share his thoughts.
So, good afternoon, everybody. Or rather, good evening now. It's beyond 5 o'clock. Thank you, Dr. Nori and Professor Prakash. At the very outset, let me first of all express our gratitude to Professor Pandey for accepting the request from our mechanical engineering department for delivering a very important lecture on additive manufacturing, and also welcome him to this distinguished lecture series started by mechanical engineering department. This has been our endeavor, sir, as it was already mentioned. 4 years ago, we started, the first batch graduated with very good outcomes, accomplishments, mainly because of the emphasis laid on research right from inception, and the quality in all respects, be it academics or non-academics, starting from academic, non-academic spaces. Because of this, there are good accomplishment in placements, in higher education admissions for first batch, and also one very good startup with a funding of $120,000. It's all because of our excellent collaborations with UC Berkeley, where students get an opportunity to spend a semester abroad. That could be one reason. I must also compliment mechanical engineering department for having done exceedingly well in research, especially, of course, the undergraduation they are also introduced the post-graduation. The first patent of this university has come from mechanical engineering department 2-3 days ago, although we have filed and published more than 20 patents. So going forward, we would like to continue this emphasis on research with guidance from people like you. And especially whenever I hear about additive manufacturing, I am reminded by additive curriculum. I still have to understand Okay, how we can derive the principles of additive manufacturing into our additive curriculum. Thank you once again. Over to you.
Thank you. Thank you.
Thank you, Vice Chancellor, sir. Now I request Dr. Jaswinder Singh, Assistant Professor, Mechanical Department, to introduce today's distinguished speaker.
Thank you, sir. Thank you. Good evening, everyone, and warm welcome to all of you. On the behalf of Mechanical Engineering Department, SRMAP, I am privileged to welcome and introduce an eminent speaker and my professor, Professor Pulak Pandey, who is working as a professor in IIT Delhi since 2017. If I speak about his academic journey, he did his MTech from IIT Kanpur in 1995, and he has completed PhD from IIT Kanpur in 2003, and after that he started his career from HBT IIT Kanpur in 1996, and after which he joined IIT Delhi in 2004, and since 2017 he is working as a professor in IIT Delhi in Mechanical Engineering Department. He also has a great research experience. He has supervised 39 PhD and 7 plus PhD still are ongoing. From these research, he also has published 190 plus publication, and he has got the citation of 7,400. And he also has been granted by the 2 patents and 1 copyright in his career. His achievements have been recognized by different awards, including 6 Gayatri Awards, Gandhian Young Technological Innovation Awards in the years of 2015, 17, 18, and 2020. And moreover, I am very happy to tell you that he is my PhD supervisor, and under his guidance, I have also got an award, Gayatri Award in 2020. Professor Pandey has a great experience in the field of additive manufacturing, non-conventional machining, 3D bioprinting, and also they have experience in the FEA analysis of manufacturing processes. So his most research experience or work and topic of today's talk is additive manufacturing and fundamentals, processes, and their application. So without wasting so much time, I would like to invite Professor Pulak Pandey for sharing his knowledge with us. And please invite him and with a whose round of applause. Thank you.
So, thank you, Jaswinder, and
Thank you,
the
sir.
management of SRM University for giving me this opportunity to address the students and also some of the colleagues from SRM University. So I will also start directly. I'll go to my slides and I'll start my lecture. So like in this field, I'm working for almost now by 20 years, you can say. So I did my PhD in this area in IIT Kanpur. And later on, after joining IIT Delhi, I am working continuously in this field. So various processes I have considered in additive manufacturing. I have guided number of students. So here today, what I will do, because most of the I think attendees are students from this university. So that's why I decided that I'll speak on the fundamentals, and I'll try to cover almost all the processes, starting from the very beginning when this concept of additive manufacturing came into existence as rapid prototyping in the beginning, and I'll also focus on the applications so that everybody will have a pretty good idea about what is the state of art in the field and what are the basics in the field and what are the applications. So then there are many projects which we have done. Projects means I generally do research work. So those research attempts, maybe if time permit, I'll try to show you something. Otherwise, I'm not going to get into that today. So let me start the lecture. So I have to share the screen first. Has it been shared?
Yes, sir, we can see it.
Yeah. So this is the
Yes.
full screen mode. Now I think you can see it.
Yes, sir, we can see.
The title is same, that is additive manufacturing or 3D printing technologies, fundamentals, applications in design and manufacturing. So first, this is the slide which I generally describe, because in order to give the students a feel that how really it has evolved, the processes have evolved, and today at what stage they are. So actually, in the very beginning, this additive manufacturing, which we are calling today, additive or manufacturing or 3D printing, they in the beginning they were known as rapid prototyping. Now, why they were known as rapid prototyping? Because if you see this typical product design cycle, then this product design cycle starts with the design need, and after design need, we try to actually in order to describe the design need, we try to capture the customer voice, and then we convert them into technical specifications. Now, after converting it into technical specifications, we try to study the relevant designs or the design solutions in that particular field, which are nearer to your problem. And later on, we in industry today, we go with the CAD process. So in CAD, we try to conceptualize the design using some softwares. Then we try to do modeling, simulation. We try to analyze the complete design by, say, finite element packages. And then we do optimization. Because any design we do, that has to be an optimum design. Then only it can form a, actually make, it may be in the form of a product. So that's what is the optimum design. We do the design optimization. Now, once somebody has optimized a design, the next and the foremost important step is to evaluate those designs, because any product you have made, you have to first make few copies of that product and you have to do the testing. Only then you will become confident that you can, you need to describe the, so what, whether really it is intending, it is actually performing the same function for which it was designed. So that's why this design evaluation becomes a very important function, and it is also a function which takes a lot of time. Now, why it takes a lot of time? Because when you have designed a new product or you have made some changes in a product, then the changes or the new product that may have typical materials, it may have very difficult to make surfaces. So because of these reasons, the prototyping or making first few copies of that particular product is a time consuming job. And sometimes the situation may be that even the technology or the way how to do that may not be known. So that's why it is a bottleneck function. Now, once your design is finalized, after testing here in design evaluation, you go for design documentation. And after that, before really going for production, there's another very important function, which is called computer-aided process engineering. So here, it's not only the process planning, but there are many other functions which include production planning, design, procurement of new tools, ordering raw materials, or if digital manufacturing is involved, you may need to develop certain codes, you need to make jigs and fixtures. So many things are needed in order to actually move to the production. So once you start producing the things, you will definitely go for quality control, packaging and shipping, and then the product comes into the market. And once the product is in the market, again you get the customer reviews and you go back and try to modify your design needs. So that's how what happens is that this design becomes a continuous process. Design of a product is always a continuous process. It never comes to an end. You are always modifying, you're always improving the design, you're always improving your product over the time. Like you can see your mobiles or your cards, every few years, or in case of mobiles, every few months, you are getting different models with updated versions in terms of software or hardware. So that's how it becomes a continuous activity. Now, in this entire design cycle, if you really see, this design evaluation is a typical function which sometimes becomes a bottleneck, because if some need is being described by the customer and you have considered it and you are unable to fabricate it or make the prototype fast, you will find that it becomes a bottleneck function. Correct? So that's why it becomes a very important tool. And here only it is the importance of the rapid prototyping which has actually shown its importance. Because if you can do this particular function in very short span of time, you may compress your entire project and you may be first few in order to gather or in order to cater the dynamic need of the customers. Correct? And you may be the best profit maker in the this competing business scenario. So that's why we try to describe that prototyping or model making is one of the important steps to finalize the product design. It helps in conceptualization of a design. Before the start of full production, a prototype is usually fabricated and tested. So earlier, actually, this activity used to be in the hands of skilled craftsmen. These skilled craftsmen used to work in the supervision of engineers, and they used to have a lot of experience. That's why they were less in number. They used to take a lot of time. Their demand was lot, and that's why this particular function used to take a lot of time. So what people thought, that why not to go for soft prototyping in order to minimize the delays. So people have tried in the mid 1970s or so. They have tried to model the things using 3D curved surfaces and try to do the virtual simulation, virtual prototyping. But definitely that is not a very good approach, because the various the actual the ground reality with reference to the particular product, because once you are doing simulation means you are solving certain differential equations, you are solving certain equations. So again, the assumptions which are involved in that simulation, they come into your way. So though you will be close to the predictions, but your predictions may be sometimes not that good. So that's why people tried that why not to go for some other way. And it was the early 1980s when people started talking about layer by layer material deposition for producing these prototypes. And this become possible due to the continuous and enormous growth in computer-aided design, computer-aided manufacturing, mechatronics, automation. All these things actually brought this kind of concept into the our industry. So this is the third and the latest trend of prototyping. It started during early 1980s or so. So the concept-wise, it is quite simple. There's nothing difficult to understand. So if you want to produce a product like this, the concept may be that one may remove the material layer by layer, the way it has been shown in this slide, or you may have two blocks which may be joined, and otherwise you may have this bulk of the material which you can deform using the dies, which is known as forming. So this is another function by which you can produce it. But in this approach, it is a bottom-up approach where in the beginning there's nothing, and you are actually adding material layer by layer from bottom to the top. And this is the kind of approach we talk in this case of additive manufacturing. So basically, in case of rapid prototyping, today we call it additive manufacturing. I'll tell you why. So it is actually we start with the digital model. Like if you really see from the definition point of view of additive manufacturing, we start with the digital model and then we slice it. And after slicing, we can cut these layers and stack these layers one over another. So we are going to have a physical prototype like this. So that's how we try to define the this digital manufacturing, and which is based on the concept of layer by layer material deposition. So we are having the CAD model, and from this CAD model, we are able to produce the physical prototype. But you can see that this surface and this surface is not matching. Is a problem here also. So basically, this these processes are actually 2.5D processes. Like from this picture, you can understand that these processes are actually 2.5D. They are not actually 3D, because along the Z direction, along the height direction, we are not doing any any approximation or any smoothening, we can say in a simple word. It is just a vertical surface which we are producing. So that's why we are actually having this physical prototype. And this is, so that's why from here to here you need to do some secondary operations in order to improve the surface quality, which is also known as stair-stepping effect in case of rapid prototyping. So this is a standard rapid prototyping chain, which is published in various papers or books, we can say. So we start with the digital CAD modeling of the component, and we save the component as STL file. And after that, this STL file is used to create the slices. So there are different softwares. You have nowadays number of even freeware softwares, open source freeware softwares, which are available. And Jaswinder knows them very well. So he has been a very key person in doing all this thing, because in the beginning, like there were very costly softwares. I don't want to take their names, but they were very costly software. Even today they are there. So they come along with the machines or suppliers, they recommend it, but definitely you can also use the freeware softwares. And after that, this data, which is a slice data, that is being fed to through a software once again to a 3D printer. Today we call it as a 3D printer, and that's how the 3D printer operates. And you get basically the deposited component which need to be post-processed. And once you do the post-processing, the prototype is tested, and if it is found okay, it's fine. Otherwise, you again go back and try to modify your CAD model. So that's how you go ahead. Okay, so this solid modeling is something which we try to understand. So this is how a solid model looks like on a computer screen. This is a virtual model. Suppose it is a machine component. Then you try to tessellate, that is the STL file. So in STL file, what we do, in STL file, we try to approximate all the surfaces of that particular CAD model into small triangles, piecewise approximation in that triangle, series of triangles. So basically you can see here I have tried to show you a free-form surface, which may be a B-spline kind of surface, and this has been approximated using number of triangles. And one such triangle I have picked, which has been drawn here as a V1, V2, V3 as the vertices of this triangle, and the actual surface is below, is this one. So like when you approximate a curved surface with a planar surface, which is a triangular surface, there's a deviation. So this deviation has been denoted by this letter delta, which is a chordal error or maximum faceted deviation. So this chordal error or maximum faceted deviation is something that is used to control the size of the triangles or the intent of, in order to preserve the intent of the design. Means I cannot go for very small triangles by considering very small value of delta. At the same time, I cannot go for very large value of delta so that the triangles are very large and the intent of the design is lost because of this approximation. So this is an intelligent decision which the designer has to take. Okay, once you are done with the tessellation, you go for the slicing. Now, what is slicing? Slicing is intersection of horizontal planes with the STL file. So once you are having the polyhedra STL file, you are going to intersect it with the horizontal planes. So once you intersect with the horizontal plane, you are going to get a nested polygon. You are going to get a polygon that and it may have even the polygon inside the polygon. So that they are called nested polygons, correct? So these one such polygon at one particular Z height is written in terms of a standard format like SLC format or CLI format. So from bottom to the top, you are actually writing every Z height, which forms one layer in terms of uh, uh, this SLC or CLI file. So basically, if you see this figure, this right hand side figure, you can enjoy that. You can appreciate that there are different slices, and these slices are of different thicknesses. So some slices are very fine, and at the same time, you can see some slices are thick slices. So what does it mean? Like generally, you will not find any additive manufacturing system which will deposit like this. But this concept of slicing is known as adaptive slicing. So this is known as adaptive slicing, and this is done in order to have minimum possible build time, because more the number of slices are, more will be the part building time. So you want to reduce the building time, at the same time you want to improve the surface quality. So that's why there will be some algorithm which will decide that at what place what slice thickness is to be placed, so that you are able to get best possible surface quality along with the building time, that is the minimum building time. So then generation of laser scanning paths or material deposition paths. So here the deposition of layers. So generation, now this technology, now we are moving towards the printer or the system, so which is depositing the material. So this printer will deposit the material by some means. There will be some technology to deposit the material. It may involve thermal heating of the polymeric material, and through nozzle it comes out and it is being deposited. Most of you might have seen that kind of printer, which is known as FDM printer, fused filament fabrication kind of technology. So here or the popular systems are laser based systems, which may have a laser beam or laser spot moves on the powder surface. So all these paths have to be calculated. So there are softwares which are freeware softwares also, and with the high-end systems, you will find that the machine manufacturer itself will supply you the software which will actually do this job for you. Now after that, once these paths are being calculated or determined, the deposition will start, because based on this calculation, there are galvano mirrors in case of laser systems, and in case of say other FDM kind of system, you have XYZ controls. So basically those paths are being calculated, and depending upon the kind of system you have, the mirror will rotate or the nozzle will move, and you are able to deposit the material. So basically there are three kinds of technologies which we have. There are liquid based technology. So the first technology from where the concept of rapid prototyping started, that is known as stereolithography. The stereolithography is something which was started in 1980s or so, and its patent was filed in 1994. Correct. So this much of time has taken. This is the first technology. So it is known as stereolithography, and I believe that because of this word only, stereo means three-dimensional. Lithography means it is in script. So you are actually writing in a 3D space, and that from here itself, this word STL has come. The extension which you call STL file, that has come from this S, T, and L. Like you may see sometimes, I never studied this, because when I attend some, I am an expert in some committee or somewhere, and people say standard tessellation language, something of this kind, people say, but I have never studied this kind of thing in any standard textbook, so I don't tell that. So I consider that this has come from STL only. And then the second kind of printers or systems are based on powder based technology. So selective laser sintering is one of the technology which is quite popular, quite versatile, and solid based materials, when we are using it, is the fused emission modeling, which is the very versatile and well-known process. Most of the time you will see this only because this is the most economical printer today. Its patent has already expired. So once you are able to do it, you go for post processing, because the part which you get from the printer, that needs to be post cued sometimes, definitely in case of stereolithography, because it works, it polymerizes liquid, so the polymerization reaction keeps going on. So that's why we need to do post curing. Then support structure. Now because you're depositing, so once you're depositing and you have an overhanging feature, you need to have a support structure, so that you have to do. And then finishing by sanding or polishing or by painting, that is again something, in order to improve the surface quality for various applications, we go ahead doing this. So what do we have, like in a very short time? If I am having a 3D printer, I can have the physical prototype in my hand in few hours of time from a virtual CAD model. So that's why we call it as rapid prototyping in the beginning. Now, over the time, like if you start looking at it, in the past 25 years or so, there has been a lot of development which has taken place in the area of rapid prototyping, and different names were given. I'll tell you that different names were given to these technologies, correct? I'll tell you in my next slide. So what kind of data, like the data which is used, one is obviously the 3D CAD and then STL. You can run a 3D printer. You can have a 2D data, you have 2D drawing, convert it to 3D, then CAD, and you can run the printer. The third one is the point cloud data. Now, what is this point cloud data? Point cloud data is something which is like if you are having an old component, you are having a very old machine, suppose in your premises, and some of the component goes down, there's a breakdown in the component. So you take out the component, 3D scan the component, the two pieces, and then try to take into the software, which is called a reverse engineering software, and join them virtually. And after that, you can make the 3D CAD in the software, you can make a STL and print it. So this kind of application is called a reverse engineering application, a very vital application, and I consider the most important application where really the potential of these 3D printers or maybe the additive manufacturing is being utilized is when we talk about biomedical applications. So in biomedical applications, we use MRI or CT scan data as an input, which is converted into STL files by some softwares like Mimix or Simpleware, and then that STL file is used to drive the printer. So that's how you can see that there are 3 to 4 important modes. I can call these two as the first mode, second and third. So these are the 3 important modes, input data we can say, by which we can start and we can run a 3D printer. So this I have already explained that if you bring this rapid prototyping technology in the as a prototyping tool in your product design cycle, you can compress the product lead time by sometimes by 90%. So this is how in various studies it has been reported that somebody can compress the manufacturing lead time so much, and that's how what happens is that this becomes an interesting tool and somebody can launch a product very fast in the market. You can create different models and you may be a very competitive, businessman in the dynamic environment. Okay, then these technologies, once again, I am coming to this, like they were named like rapid prototyping, generative manufacturing, solid freeform fabrication, rapid prototyping, correct? Layered manufacturing. So many, titles came for this technology. But today, it has settled down to 3D printing or additive manufacturing. Now, if you really want to understand the difference, I say that if I am using a small system which I can keep in my office or in a small lab kind of environment, and it is a small system, tabletop system, then I call it as a 3D printer. But if I use a big machine, big system in an industrial environment, the system may be as good as a room. It may be as, the size may be as maybe 20 feet by 20 feet by 20 feet. If that kind of system 3D printer you are having and you are using it for industrial production purpose, for customized fabrication, you may call it as an additive manufacturing. It may be a metal based system which are more latest. It may be, polymer based systems also. So I'll explain all the things in my forthcoming slides. But if you want to classify these AM techniques now, again, they go with the solid or liquid based. So liquid based was very first developed. It is based on the concept of polymerization, and the polymerization may be based on thermal, it may be based on UV lamp, solid ground curing kind of system, or it may be based on laser, which is stereolithography, or based on holography. And if it is a solid, then the solid material may be either in the form of wire, as you have seen in FDM. It may be in the form of powder, one powder or a mixed blend of powders. So it may be a process like selective laser sintering, or it may be a foil also, correct? So I'll show these things. Now you can see here I have written a word 3D printing. Actually, what happened in between, that somebody brought a printer and they named their technology as 3D printing. And this word has actually picked up so much that it has become some sort of so popular that every process is now termed as 3D printing, correct? So this is the first process which is known as stereolithography. Here what is being done is that the key here is the material actually. The material is a photosensitive monomer. Now monomer is basically small molecules. They are not long chain molecules. But once they are acted with laser, that is the photon, then what happens? There's a free radicals which are being formed and they join actually. That is called a polymerization process. So a low molecular weight monomer that gets converted into long chain high molecular weight molecule. So that's how it becomes a polymer. So here you can see the principle is simple. There's a platform on which you are pouring the photosensitive monomer and just equal to one layer. And then you have already calculated the data. So this galvano mirror, it will reflect the laser spot over the surface of this layer, monomer layer. So wherever the spot will move, below which there will be a polymerization reaction, and a solid voxel will be deposited. So once you are done with one layer, this platform will go down. You will do the second layer, then platform will go down, and all the data has already been calculated through the software, which is actually rotating this mirror, movable mirror, which is a galvano mirror, and that is doing the job for you. Now in this picture, I have shown this is support structure also. So if there's any overhanging feature present in the component, one has to deposit the support structure also. If you don't do that, there will be a problem, because what you will do later on, because there's nothing on which you are going to deposit, correct? Because all other portion will be a liquid portion. So one has to plan for the support structure, and all these standard softwares which you are having, even the open source freeware softwares, they provide you this facility that you can select a proper support structure, and their density and their type, everything is there which one can select. Okay, after that, the other versatile system is called laser sintering, selective laser sintering. Now this sintering is very much different than the conventional sintering, what you may be knowing in powder metallurgy. Here we do not apply any pressure. There's no compaction, nothing. What you're doing is simply, spreading the layer of the powder, and this layer of the powder is as small as maybe 100 microns, 150 microns. So in this diagram, you can see this is a very thick layer I have shown, but it is actually 150 micron. You can imagine how small, how thin it is. And then the similar principle, you are having laser, you are having galvanomirror, and the laser spot moves. And when the laser spot moves, these fine particles of this polymeric material or maybe the metallic material they are going to melt and fuse. So they form a closed lump kind of thing. And wherever the laser spot will not go, that will remain as a powder. Correct? So in this case, what happens is that you need not to plan for support structure, because the powder which is present there, it is in solid form, that will act like a support structure. So that is an advantage of this process. You need not to plan for the support structure in this process. Then there's another important point, that you can have polymer material, you can have a metal material, metallic materials, provided they are available to you in the form of powder, fine powder. So one can play with number of powders in this particular process. So that's why it is a versatile process. The strength of the component is sufficiently good. The surface quality is also mediocrely good. It's not definitely as good as the stereolithography, but definitely it's not so bad also as FDM. So that's how you go ahead with this process. I will show you another slide also. Here you will understand in a better manner. So generally this process is done in the closed chamber. And in case of polymeric processes, in high-end machines, you will find they maintain a nitrogen environment. But in a low-end machines, you will see that even in a normal atmospheric environment also, one can do. And this is the powder spreading by recoater. So the powder is spread, then there's a powder bed exposed to laser beam. So here this brown color, this shows the that this is a solidified material, and the yellow color is actually the powder. So this yellow color thing will act like a support structure in this case. Then the platform moves down, and then you again recoat, and that's how the process keeps going in this particular process. So here the important point to be noted is that if it is a metal machine, we call it DMLS or a selective laser melting. If it is a polymeric machine, we call it a selective laser sintering. This is just, the principle wise they are same, only the difference will be in terms of temperatures, because if it is a polymeric machine, we hardly go up to 250 degree Celsius temperature, and if it is a metal machine, we go for up to 1300-1400 degrees Celsius temperature, because in metal machine we need to deal with stainless steel material, nitinol, that is a shape memory material, super alloys like Inconel, even the titanium medical grade alloy like TiAl V6 kind of alloy. So all these are the materials, steel, stainless steel, then this chromium carbon steel. They are very useful steels for implant purposes. So all these things are being fabricated in this particular additive manufacturing technology, which is called selective laser melting. Then everybody knows about it. I believe you may be having this printer, which is known as fuse depression modeling. So this particular printer is very simple. There's a spool of thin polymeric wire, which is generally ABS, and there are counter rotating rolls through which you are pulling down this wire, and this comes out. It's a molten ABS material, and you are able to deposit the these rails on this platform. And usually you will find that there are two nozzles in a printer. So one is for this ABS material and this for the support material. And later on, you have to remove the support material by mechanical means or by dissolving it in water or maybe in some other solvent, which may be a organic solvent. Okay, then this is called laminated object manufacturing. Not a very popular system. Here we are using actually sheet material, correct? So this sheet material is used, and you are actually, what you are doing on this platform, you are putting this sheet, and this roller actually rotates. You are putting the sheet, and this is a laminating roller. So this roller will move, and this will get stick to this platform. After that, there is again laser. So here the function of laser is to cut the material. This is a very important point. Like in other case, the idea of laser was to melt the particles and fuse them together. Here the idea is the laser is used to cut the material. So definitely the laser optics will be little different. If you want to melt, the laser spot has to be bigger. If you want to cut, the laser spot has to be quite smaller. So that's how the laser optics is little different. And you're cutting here. So now you can see here that this particular annular ring which has been shown is something which is required, and all other portion is a waste portion. So once it is being done, this will move ahead. The next portion will come. Again, the laminating roll will move. It will stick to the first layer. Again, the laser will come from the top. It will cut. So finally, it will keep on building. And what you will get a block. From this block, you will remove all unwanted cubical pieces. So whatsoever is left is actually your model. So this particular manufacturing technique, which is called LOM, laminated object manufacturing, is something which is, I'll say, used to make mock models. It is because the resolution is low, and you have a small component you want to display it. So you can make a bigger model using this polymeric sheet, which can be used to demonstrate to the people, to the students, to the professionals in that area, if you want to explain it to them. Okay, then this is called powder blown technology. Now this particular method is called powder bed technology method, because you are using powder bed here. But the latest trend is powder blown technology. What is powder blown technology? Here we are using a conical nozzle or maybe some pipes. I'll show you the video also. So here, from here, the powder comes like this from the sides, and there's a laser beam from the center. The interaction gives you the material that gets melted, and then you are having the either XY movement, you are giving it to nozzle or to the platform, so you're able to deposit the material. So you can see these kinds of materials have been deposited. Now the best point, the good point here is, now this is called, the title of the process, laser engineered net shaping. This process was developed around 2006 at Sandia National Laboratories in US, and there were many parallel developments in US, like Michigan University also developed similar kind of system. They named it DMD. They named it direct metal deposition. Today we have number of systems which are based on this kind of concept, and we jointly call them as direct energy deposition, DED. They are named as, we can call it, sometimes I do not agree with this kind of acronym, DED, direct energy deposition. You cannot deposit energy directly. This is a material deposition, but people call it direct energy deposition. Anyway, so you can see the kind of geometries with thick walls or with thin walls they have been produced, and the different materials have been processed. And here the good thing is that generally you are having 4 tips, like there may be 1, 2, 3, and 4 from the back side. So 4 channels are there. So you can have different materials flowing down, suspended maybe in argon gas, and because it is metal, so you have to have a environment of inert gas. So they come down. So you can change the flow rate, you can change the material, switch from A to B. So you can create a functionally graded compositionally functionally graded material with this kind of system. So this is one of the most, but I'll say to me, I am very much fascinated to this technology personally, because to me it appears it has a lot of potential, and we have I think very few machines, 1-2 machines only in our country about it. But the limitation here is definitely the surface quality and accuracy. They are lower as compared to the powder bed technology. But it has additional advantages of making functionally graded material or repairing of the objects. Like this is a wheel which is worn. So I can use this lens kind of technology with a, definitely we have to use CAD model and do some all that digital things. And after that, we can repair the model. Like there may be a turbine blade. The turbine blade has got some pit, some material has worn out. Correct? It has eroded because of the jetting action of the gas or maybe the kind of turbine it is. So you need to fill up that particular pit. You can use this process to repair that blade. Then, so this is a process, I'll say window, or what we call its interface. This is how the interface looks like. But in case of powder bed technology, this is how the interface looks like. The powder is spread and the laser is coming from the top. It is interacting with the material, and this is how the texture changes. This is unsintered powder, and this is where the laser has already fallen. So it is the sintered zones. Correct? So this is how you can create a component in case of SLM kind of process. So let me go back to another set of slides where I'll show you the advanced processes now. Okay, so you can see that these various processes which I would like to describe now. Direct energy deposition. So this is how the lens I have already told you, which falls in this category. So these are the channels from which the powder comes down, and this is a laser with optics, and you are able to deposit the material on this. There may be a control. For controlling, you need pyrometers, you have to have inert gas atmosphere, there will be infrared thermometer or camera to monitor the zone. So many things are there. Now, there will be coaxial nozzle mounted on multi-axis arm. Nozzle can have tilting mechanism with z-axis movement, and materials melted and deposited with a laser or electron beam. So you can see this video. You will enjoy this video. This I have taken from this particular source, which the reference has been given below. Okay, then we can, this is another illustration of direct energy deposition. This is a, we can say, virtual simulation kind of thing. So okay. So here we can say that we can create the components, parts directly melting materials and depositing them on the substrate, mostly used with metal powders or wire source materials. Materials melted using laser. Upon deposition, further materials added layer by layer. Correct? So here basically what happens is that they're suitable for fabricating multi-graded materials, large size components, coatings, and they have fast build and rapid metal depositions. So as compared to SLM process, that is a powder bed process, this has a very fast deposition. Correct? But accuracy wise, you will find it is little lesser and the quality of surface is little inferior. They're fully densed part, no need of supports because you are having tilting mechanism and can be used for repairing also. So these are the, some cons I have already explained. So this direct energy deposition has a variety of applications in the various domains like aerospace, automotive, repairing component, nuclear, in various industries. You can imagine, it is up to you, like where, in which field you want to use it. So these are some acknowledgements for I have taken this material. Then LMD is another process. Like I told you that several developments have taken place simultaneously. Similar, they have different design of nozzle, like, but similar concept. The laser comes, there are two streams of powder and you are depositing this way. So again, the similar kind of pros and cons we have for this process. We call it laser metal deposition process. So here actually we can say that we have complex process structure property relationship. The thermal histories are very complex. Anisotropy is something, which is there in the material or the structures, correct? And they are very expensive. Like if you really see one machine cost after discount to system like ours, it will come not less than 3.5 to 4 crores Indian rupees. Correct. So that's the, and that is a small system. It's not a industry grade system. It will be a lab based system. So that's how these are costly. Then we have another system which is called electron beam system, EBAM, electron beam additive manufacturing. So here it has both the versions actually. There's a powder bed. Instead of laser, we are having electron beam of high energy, that is around 3 kilowatts of an electron beam. So, and the process has to be conducted in vacuum. It eliminates impurities and yields excellent mechanical properties. So it is a very, I'll say, quite recent process. Then we have another version where we have wire based. So instead of having powder bed, we have a wire feeder and there's an electron beam gun, and that's how it, so everything will be done in vacuum. So you can again imagine the cost of the system. It will be definitely higher. But here the good thing is that you get very, few AM technologies capable of making fully density functional components. You can create fine features here because you're doing electron beams you're using, correct? And again, can efficiently assist development and modifications of products, especially for complex, difficult to fabricate components. The residual stresses are low as compared to other ones, based on as compared to laser based processes or maybe wire arc additive manufacturing, which I'll show in the next slide. So different components, different domains where you can apply, starting from turbines to nuclear to medical to cladding to power generation to marine propulsion. So this is the technology. Then wire arc additive manufacturing. So here welding process is used actually. MIG kind of process is used to deposit the material as it has been shown in this particular video. So you can, so they all classify, they are come in the category of direct energy deposition. You can see this video on BAM. Okay, so this is how, you know, the surface is being built in case of BAM process. You can see it's quite coarser. So here you have wide range of depositions. Conventional machining is needed. There's a reduced lead time, good structural integrity, but residual stresses are more. Shielding gases definitely are needed if it is a reactive material, low resolution. So you have to do machining for finishing these components. These are some examples of BAM. Then we have one latest machine that is called multi-jet fusion printing technology by HP. So this is also not very old system. Here, they deposit actually plastic. Once again, ABS kind of machine material which is being deposited. Like, but here they are not using laser, but they are using actually UV, and they are using two chemicals. One they call as detailing agent, and another is called fusing agent. So there's a layer of powder, and on that layer of powder, they are detailing, and then they are putting the fusing agent, and in one go they just push this lamp. This is blown. So what happens is that you are able to do the curing in one go, one shot. So that's why it is a faster printer. The accuracy is good, quite good, and you can see that this is a flexible material that can be printed. It's a polyurethane, and polyamide material parts with very high strength, they can be printed. So these are various components you can see which are being done by this HP printer. Then DLP is another technology which is it is again, I have come to know about it few months back only. So here again the concept is
DLP
like this.
printers use a light projector similar to what you would find in a movie theater to project the image of an entire layer simultaneously, regardless of the number of parts. Because they cure a full layer in a single flash, DLP printers can be outstandingly fast. They are also very reliable with low complexity and no movement.
Yeah. So this is the system actually. So in one go, you are covering the entire layer. Like means in case of stereolithography, there will be a point that will move. But here in one go, you are covering the entire layer as you are doing in case of movie projection. So you can see here that in SLA, this spot, laser spot keeps moving. But in this case, the one layer will go in one way. So here also you are using photosensitive monomer to print. But I think because there's a lot of competition now, if the sections are large, then this may be faster. But if the sections are thinner, there is a lot of intricacy, then SLA may be better. So it will depend on the situation, that in what situation, which one will be a better system. So different, you can see there are different applications which people have kept on their websites or various sources which I have picked up from there. Then another important process is called two-photon polymerization 3D printing technique. It is for mainly for medical, it is for making micro components actually. So here the concept is there's a conical laser beam. So the concept is that once the laser is conical, so energy intensity here is suddenly becomes very high. So in this zone only there will be polymerization. So I can focus in such a way that I can deposit a voxel, a volume as small as of 100 nanometer size. So that's why it becomes a very interesting process. And what we do, we get here high resolution of the order of 100 nanometer. It is a complementary to two-photon microscopy. There's an online process observation which is available, and we have polymerized in the presence of biology. Now, this is an important feature because our biological tissues and cells, they are much larger than this 100 nanometer. So you can do polymerization in the presence of these biological tissues, but you need to have biocompatible initiators. You need to have monomer with low toxicity. So it has also a number of applications in different zones, different technologies, including metamaterials, tissue engineering, photonics, MEMS, microelectronics, etc. So some examples, once again, they'll excite you. These are prisms. These are micro prisms. The dimension you can appreciate, 60 micron is this. So these are small prisms. This is a lens which is having 23 micrometer is the, this length. So it is around, we can say 100 micrometers the diameter of this lens. And this is a biological scaffold for cell biology. The kind of sizes you can appreciate is 100 micrometer or so. And these are the micro needles for drug delivery. So again, the sizes you can appreciate. So the kind of potential this process is having, correct? Then we have another printer which is called mark forged printer. It is used to deposit composites. So it works on the principle of fused filament fabrication only, but very precisely developed machine where very fine spools of nylon or carbon fiber or maybe some other kind of fiber, they can be deposited alternatively, or there may be material which is called onyx, which has a chopped carbon fiber. So you can deposit Kevlar, fiberglass, etc. So alternatively, you can have particulate kind of situation. So you are able to do a lot of things with this kind of printer. Now you can see the kind of applications which are present. With this printer, we have this printer at IIT Delhi, and we can produce these kinds of workable components, which are working actually components. It's a shock absorber, it is a carburetor, it is a jaw to hold the something for during machining. So these are the working, plastic components, composite components, but they are directly usable. So like today, what happens is we started with rapid prototyping, which was a very, I'll say, initial process, primitive process. And today we are even able to print composites, and we are having, metallic printers where we are making implants, we are having composite printers, we are making, these kinds of components. So today we are calling this technology as additive manufacturing technology, because it is no more a design tool. Though it is a design tool also, but today it is a manufacturing solution also for various, kinds of technologies or technological solutions it can provide for various kinds of problems directly, correct? So with this, I'll stop here. I think I have taken sufficient amount of time, and if there are any question, I request the audience to please ask. Correct?
Sir, thank you very much, sir. The inspiring talk. Students and faculty in the audience requested to Any questions? Professor Pandey? Please raise your hands so that ITKM team can.
Sir, I have this one question. This is recently, this is the recent phase additive manufacturing. So, in reality, we are not seeing whether the parts are going to survive for a million cycles or maybe 20 years lifespan. So, regarding that, what is your comments?
Metallic components are being now, implants are being built. They are like knee implants are there, hip implants are there. Correct? They are done by electron beam machining, selective measure melting. So they are for lifetime. Correct? Like definitely mechanical components if you are making, for example, aero components, defense components. So the standards are not yet developed. Correct? People, there is the development of standards for additive manufacturing, especially for metallic thing, that is an open area because a lot of work is going on and people are trying to develop standards the way we are having standards. Correct? So once those standards comes, you will get answer of your question.
Okay. All right. Thank you. Okay, I think with the interest of time, I think Norris sir can.
I have. Good evening, Professor Pandey. It was really an inspiring and mesmerizing talk, giving us better insights into 3D printing. This is faculty from Thermofluid Engineering of SRMAP in the mechanical department. So my question is twofold. I hope I am allowed to ask two questions, Dr. Noori.
Yeah, please.
Okay. So the first thing is with this rapid micro channels or microfluidic manufacturing with non-metallic or PDMS based micro channels, which are being used as micro TAS or lab on chip devices. How easily can 3D printing or additive manufacturing?
I believe for those things, stereolithography or the micro stereolithography is the best solution.
Okay, fine, sir. That is there. So suppose if we can send a geometry to you in your lab, so is there a facilitation so that we can get micro channels fabricated?
Micro machine we do not have.
Okay.
We are having, like, you can discuss with Jaswinder. He knows everything that what can be done here.
Yes, sir. So the second question is in terms of lot of thermal part involved in the fabrication process. As we can see, you explained the several techniques, selective laser based and all. So when you have this slurry based or dropping technique in which from a nozzle some non-Newtonian fluid is coming out, be it either plastic or metallic. So this thermal characterization of that, how do you feel? Is there a huge scope to work in that area?
Actually, I'll tell you that there are faculty members who are working in this kind of work. The kind of thing you are telling, they are trying to model the phenomena using some abacus kind of or safety kind of packages they are using and trying to model.
Yeah.
But definitely you can do it. But that may be a good thing for later developments, because today I believe that these things have been done by experimental means, correct?
Yes.
Or by optimizing the system through design of experiments. That's how statistical means have been used to arrive at a good solution. But if you offer a physics-based model or a numerical solution based on the process physics, that may be good idea. So people are actually working, but it may be good for future development. Otherwise, already machines have been developed. So that is also one of the points to remember, because that becomes a very academically challenging work.
Yes.
But at the same time, because a lot of assumptions are there in these models. So sometimes you will find that practically they are not that significant. But
because as I see as a thermal engineer, the challenge lies in transient analysis.
Yeah, I understand. I did, like in my master's work, I did a lot of finite element and I solved a problem. You will you will sometimes, you may discuss with me
Yeah.
the kind of problem I have solved. That is a transient heat transfer
Yes, sir.
problem with spark, and the spark location changes randomly on the workpiece. It is a transient, non-linear problem with variable location heat source.
Of the heat source. Yeah, yeah.
And the heat source location is a random location.
So, but have you continued working on that with some student now also in your lab, or?
I actually left,
Okay.
I did as an MTech student. My paper is there. Jaswinder knows about it. So you can see that paper. I believe even today you will not find any commercial software which can solve that.
Yes, truly. What you're speaking is true, because we tried for something last 6 months. It didn't work
So
out.
I wrote my own, Fortran code in 1993 to 5 and did my MTech there. So after that, I realized that after putting so much of effort, at the end of the day, you end up with some equations, and then finally you say that this is not coming closer to the result because of these reasons, and everybody is happy about it, and you get a degree. So I realized that it is better to do something which appears on the ground.
Yeah,
so,
yeah.
So like my PhD has been more on the algorithm developments for 3D printing, and only 20% work I did, which you can call as a validation kind of thing, which was experimental. But today, I do a lot of experiments.
Oh, great, sir. Great. Nice to hear from you. And we would love to have you physically in our campus sometime when things comes to normalcy for discussions and collaborations in future. Thanks for answering the questions.
It was a nice discussion with all of you, and it was a nice opportunity for me to interact. So thanks to everybody, Professor Jadhav and Professor, I'll say, Professor Venkat. Yeah. Our VC is there. He was there. I think he's left, and definitely Jaswinder is there. So.
Yes, sir. And I really enjoyed, sir. Listening to you, I really enjoyed.
Sir, may I request one or two questions from the students? I mean, students, do you have any questions?
If students have questions, they can ask. Yeah.
Yeah. Please raise your hand. Okay. So, okay, we have Hassan.
Good evening, sir. So I was basically read about a lot of progress in 3D printing technologies. So even for the Mars mission by you might have heard about this Mars mission, right, sir? So there is this technological developments that were going on in 3D printing that there you can build out proper houses or proper bases in Mars. So what is your view on that, sir? Is it possible that technology can go to that scale?
No.
3D printing technology.
You are talking about mass manufacturing.
No, sir. In the Mars, sir, you know the planet Mars, right?
Mars.
So, yes, sir.
Actually, these questions are very interesting, open-ended questions. And when you become a sales engineer, you have to talk like this only. Is it okay? But definitely it's feasible. I'll not say it is infeasible, but it's not. People have not yet done. People are only talking. Correct? That yes, suppose I go to an this what do you call space center.
Yes. Yes. Sir.
And you take a 3D printer with you, and instead of carrying spare parts, and you can print those spare parts there. You may be having the solid models, and you can print there if something goes wrong. So these things are definitely. I cannot say that it cannot happen, but once when it will practically happening, you have to wait for some time.
Okay, sir.
Thank you, sir.
Okay.
Thank you, sir.
So I'll request Dr. Jaswinder to deliver the vote of thanks.
Okay, thank you, sir. So I, on behalf of SRM University Mechanical Department and entire fraternity of the university, I extend a very hearty words of thanks to Professor Pulakmohan Pandey, who spared time from his busy schedule to grace our occasion and lecture. Today's lecture was full of the knowledge and interesting facts about the additive manufacturing. It gave deep insight into the topic and also revealed some interesting facts about the additive manufacturing. I'm pretty sure that precious knowledge that Professor Pandey gave us will definitely help all of us in future. So at last, I'm very thankful to Professor Pulakmohan Pandey for letting us with the great experiences of his researches. And I also thanks to all of the participants who give their time for this lecture. Thank you. Thank you.
Thank you.
Yes,
Thanks a lot, everyone, for your kind invitation and the interaction we had. I really enjoyed today's evening. So now I'll go back to my home. Thanks a lot.
Okay, thank you,
Thank
sir.
you, sir. Thank you very much.
Thank you, Pandey sir.